Hey guys, Mr. Betts here. Let's take a look at an example where we can use a couple of different methods to find the area of a region. And just like any other area problem, first thing we want to do is figure out exactly what region we're finding the area of. So we are given three functions here. So it's the area of the region bounded above by y equals 2 plus the square root of x, which is this red function here, below by y equals 2 minus the square root of x, so that's the blue one here, and to the right by x equals 4. All right, so that bounded region, it's the only bounded region by all three of those. All other regions defined by those are going to be unbounded, is that area that I have shaded there. So what we're going to do is we're going to write two integral expressions, one with respect to x and one with respect to y, that will find this area. We are not asked in this problem to choose either to evaluate or to evaluate both of them, but we will talk in the end about why we might write both of them, and then we could choose one to evaluate. So with respect to x, our Riemann sum rectangles are going to be vertical. So with respect to x, we're moving along the x-axis, and we're going to get rectangles that look like this. So when we have a region that's bounded above and below by separate functions, remember we're always going to do top minus bottom. So with respect to x, we're going to integrate from our lower limit, which is x equals 0, to our upper limit, which is x equals 4. And then we are going to take the upper function, the top, minus the lower function, the bottom. So the top function is going to be the 2 plus square root of x. The bottom function is going to be 2 minus the square root of x. And even though we're not going to evaluate this, I'm going to go ahead and simplify this expression because it would be a lot easier to evaluate if we do. So this is going to be equal to the integral from 0 to 4 of the 2's are going to cancel each other out. And so it ends up being just square root of x minus the opposite of square root of x, which is going to be 2 square root of x with respect to x. Not a bad integral to evaluate. We can write that as 2x to the 1/2, and then using the power rule, we can take the antiderivative of that pretty easily. With respect to y, our Riemann sum rectangles are going to look like this. Now, at first, it may seem like our right and our left are going to be different. However, you may notice that this right here, these two together are essentially just a sideways parabola. And indeed, if we solve both of these for x, we're going to get y minus 2 quantity squared. So I'm going to go ahead and do this. Take this one, subtract 2 from both sides. So we get square root of x equals y minus 2, and x equals the quantity y minus 2 squared. If we do that with this one, we get the opposite of the square root of x equals y minus 2. And then we don't have to really get rid of the negative there. We can just square both sides because that will take care of the negative. And so we square both sides and we get x equals quantity y minus 2 squared. So the idea here is actually the top half and the bottom half can be written as a single parabola, a single function of y. So single function x with respect to y. And so we can use that single function as the left function. So our Riemann sum rectangles, remember, with respect to y, we always want to do right minus left, because along the x-axis, right is greater and left is lesser. So that area then, with respect to y, will be the integral from the lower y value, which is 0. That's given by the y value of this intersection here. And then the upper limit will be the y value of this intersection here, which is y equals 4. Those you can confirm algebraically if you want by setting this equal to this for the upper one and this one equal to this one for the lower intersection. And then we're going to do right minus left. So the right function is going to be the x equals 4 minus the left is going to be this y minus 2 quantity squared. And this is going to be with respect to y. So this integrand here gives the width of the interval, of the Riemann sum rectangle, and the dy gives the height of the Riemann sum rectangle. Now, taking a look at these two integrals that we wrote, this one with respect to x and this one with respect to y, doing that work to write this with respect to y didn't actually end up giving us an integral that's easier to evaluate. So if I were going to choose one of these to evaluate, I would choose the one with respect to x. There are a lot of situations, though, where when we do this, we get a much simpler one with respect to y. And so by doing this with respect to y, we can write an expression that's a lot easier to evaluate than the one we would get with respect to x. One more thing I want to point out here, just more reiterate than anything, these limits here with respect to y are because we are going from 0 to 4 along the y-axis. And these limits here are because we are going from 0 to 4 along the x-axis. So it just turns out that the region that we're finding the area of is bounded in the square. But very often we will get different limits with respect to x and with respect to y. So whatever the differential is here is what these limits need to be.